Hello and welcome to this lecture. So in this lecture, we're going to start looking at solutions for linear equations, but we're also going to try and relate it to span and dimensions. So far we've learned about vectors and how vectors are connected to linear equations in some way, and then what is span of of a set of vectors, what is a subspace, etc. All of that we've been seeing. Let's take some examples of linear equations and then try and connect them to the spans and then see what that means. So it's sort of like an exploratory thing. We'll look at a lot of examples and ask some questions to see how span and dimension may be connected. So let's get started. So here is a very simple example. I'll do a whole bunch of examples, and some of them in the beginning I'll do in some detail and then go through it a little bit faster later on. So here's a simple set of linear equations, three variables, right? X, Y, and Z are the variables. There are three simple equations, very small coefficients. All of us know how to solve it. How do you solve it? You start by eliminating, right? So your usual method, I'm going to call it the usual method of solving equations, which is by elimination. I mean, you may also know some matrix type method, but I'm not going to talk about that here. We'll use elimination, right? So I've taken the second equation minus the first equation. So I get y plus 2z equals 3. The third equation minus the first equation, again I get y plus 5z equals 6. Okay. Then what's the next step? Again, you can eliminate y from the second and third equation. You subtract those two, you get 3z equals 3, and you're done, right? So at this point, you're done because you know z is 1, and then you back substitute as there, you get y is 1, and then y1, z1 will also give you x1. So from here, you can go to the unique solution, which is just a single point. A single point in my vector space is said to have dimension 0 in some sense, right? So dimension of it is 0. It doesn't have, a line has dimension 1, a plane has dimension 2, one point has dimension 0. Okay. So this seems simple enough. We're going to slightly complicate this a little bit and give you a picture of how to think of it in terms of spans and dimensions and all that, right? So we know in terms of span, this problem, this linear equation problem, talks about the span of the columns of this matrix, right? There are three columns here in this matrix, 1, 1, 1, 1, 2, 2, and 1, 3, 6, right? The columns of these three the columns of this matrix, the three columns, if you multiply the first column by x, second column by y, third column by z, you should get 3, 6, 9, right? So that's the matrix multiplication meaning of this. We've seen this before. So let's focus on this matrix alone and these three columns, okay? How do you find the span of these three columns? Okay, so to know more about the span of vectors, it's good to once again do elimination. Okay, but instead of row wise, we're going to do column wise because I'm interested in the span of the columns. So this is one little change when you go from equation to matrix. You're writing down the coefficients normally like usual, but then you have to think of the span of the columns, which means you have to write down the columns as individual vectors in the subspace and then do elimination to figure out an easier basis. Okay. So that's the first step usually. So how do you do that? You think of span of 1, 1, 1, which is like the first column, and then 1, 2, 2. Notice that is the second column, okay, and then 1, 3, 6. So the question you're asking is, what is the span of these three vectors? Okay, so this is sort of like the linear algebra view. The span of these three vectors, according to my solution, okay, what I did here, actually contains 3, 6, 9, right? So that's what this means linear algebraically. This equation that you solved and found solution 1, 1, 1 using your usual simple elimination method actually told you that the span of 1, 1, 1, 1, 2, 2, and 1, 3, 6, right? The span of these three vectors we know is a subspace, and it contains 3, 6, 9. That's what it says. Okay. So we can do elimination here to get this into a better set of bases, better basis, right? 1, 1, 1, 1, 2, 2, 1, 3, 6 is not a nice enough basis. So maybe we can get a better basis, and from there maybe we can know more about the span, right? If you know more about the span, maybe it will be clear to you that 3, 6, 9 definitely belongs to the span without even solving. Okay, so how wonderful that would be, right? So without even solving, without doing all these steps, if you can know just by the span that 3, 6, 9 has to definitely belong to the span, that's a nice thing to know. Okay, let's see if that is true. Okay, so if you do elimination, you do the elimination the way we described it here, you will end up with a basis which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so this is the first time we're doing this in this example. I'm going to show it to you in some detail, but later on I may not show all this detail. So 1, 1, 1, 1, 2, 2, 1, 3, 6, right? So that's my vectors that I have. Okay. So, what would be the first step in the elimination? I am going to say row 2 is row 2 minus row 1 and row 3 is row 3 minus row 1, right. So, this is my pivot. I am making everything below the pivot 0. So, I am just subtracting this out. So, I will end up getting first row remains the same, second row becomes 0 1 1, third row becomes 0 2 5, I am sorry, right. And then what's the next step in the elimination? You've got all these zeros accomplished. This is 1, that's also accomplished. Then you move to the next one. Your pivot is this 1, and now you have to make this guy 0. How do you make this guy 0? You make row 3 as row 3 minus 2 times row 2, right. So, if you do that, then you will have the first one as it is, second guy 0 1 1, and the third guy becomes 0 0 3, right. So, now after you get this lower triangular form, right, after you've got all non-zero elements in the lower triangular form. In fact, this 3 you can make 1 also. You can divide by 3, divide the last row by 3. You can do that, right. So, maybe we do that, right. So, you divide row 3 is row 3 by 3, and you get this very simple form. I am doing it in like glorious detail here. We will skip the details as we go along. Next, once you got this this triangle finished, you can go above this triangle and then once again make those guys 0. So, how do you do this? These two how do you make them 0? I am going to make row 1 as row 1 minus row 2 minus row 3. Okay. So, if I do that, I am going to get 1 0 0 0 1 1 0 0 1, and likewise finally row 2 is row 2 minus row 3, right. So, that makes this guy subtracted with this, you will get to 0. Okay, 0 1 0 0 0 1. So, I started from here and I ended up here, right. I started by saying I am looking at span of 1 1 1 1 2 2 1 1 3 6. That has to be the same as span of 1 0 0 0 1 0 0 0 1. Okay. So, this is this elimination step. It is also called this is called the row reduced echelon form. This is a very famous word, RREF. Okay. So, from here if you go to the row reduced echelon form, you get this, and that gives you the same span, right. So, this is what we learned before. So, you get here by this elimination process that the span of the columns of this matrix is actually the span of 1 0 0 0 1 0 0 0 1. Okay. From here we learn that this span, okay, this is very easy at this point, right. At this point, if you have 1 0 0, this is a standard basis. The span of these things is R3, the entire R3 space. So, what does that mean? The span of these 3 columns contains every single vector in R3, every single vector with 3 coordinates. It's there and it's got a dimension of 3. Okay. So, clearly from this we can conclude not only for 3 6 9, whatever you put here in the RHS, whatever vector you put in the RHS, this equation, as long as you do not change these coefficients here, this equation is going to have a unique solution, exactly one solution all the time, irrespective of the RHS, because this rank ends up being 3, this dimension ends up being 3, the dimension of the span of the columns is 3, and that is the entire R3, which means any vector on the right hand side I can obtain by multiplying this matrix with some suitable vector on the right. Okay, 1 1 1 is particularly nice, it gives you 3 6 9. But if you do other things, you will end up getting all possible vectors. Okay. So, this picture you should sort of keep in mind how when you solve one equation, you have one method, but then when you do the linear algebraic view, you learn a little bit more about the equation. You learn that for all RHS, there has to be a solution. Okay. Let us play around with this. I want you to think about this dimension 3, that is the span of this subspace, column space, so to speak, the space of all columns, and then the solution ends up being a dimension 0 solution. So, we will see more examples now. I will show you more examples with 3 variables and 3 equations, where it will look dangerously similar to this one, but then the nature of the span will be different, the nature of the solution will be different. Let us take a look at that. Okay. Here is the next example. I am not going to do the elimination steps in detail here. I will go through them a little faster. I will let you do it, work it out on your own and try it. So, that will give you some practice as well. So, here is the equation. So, if you notice from the previous equation, I have changed this 6 that was here to 5. Okay. It's the only change I did. I did not do anything else. I changed it to 5. But notice what happens when you try and solve this. The first step goes through exactly more or less the similar one. The second step, interestingly, will give you 0 equals 0 at the end. Okay. So anytime you have something like this, something interesting is going on. Okay, so you should be always alert to these, getting these zeros. When you get these zeros, something interesting is going on. So you actually only have 2 equations, and that's how they end up. Okay, so how do you solve these kind of equations? We have seen this long ago in another lecture, how to do this. There are x, y, and z. So these kind of variables, the z variable is called a free variable. You can pick it as anything you like. Normally what would you do? You would pick that z to be equal to u. Okay, you put z equals u here and treat u as a constant, right? Take it to the right hand side and solve the equation with just x and y. If you do that, you see y is 3 minus 2u. That's what you get here. And then plug back in here, put z equals u and y as 3 minus 2u here, and you will get x equals u. Okay, so you can see that that's how it works out. Okay, so u 3 minus 2u, u for any u in R is a solution to these 3 equations. So you have 3 equations. So notice the contrasting nature here. So in fact, this one you can also write like this. You can write it as 0, 3, 0 plus u times 1 minus 2, 1. Notice this form. We have seen such forms before when we solve linear equations, but anyway, I'm reiterating it. So you have one free variable here, and this ends up being some sort of a line in R3. So you get a dimension 1 solution for this equation. It's not a dimension 0 solution. Notice how different it is. I just changed one number, one coefficient, and the solution, instead of being dimension 0, magically became dimension 1. Okay, is there something going on here? Let's try and look at this thing. So here I've written down the columns here and the columns, but notice this is sort of symmetric. Whether you take rows or columns, you get the same thing. It's a bit interesting, but nevertheless, let's think of the columns here. Okay, and then I'm asking the question span of 1, 1, 1, 1, 2, 3, 1, 3, 5. If you do the same reduction, elimination that we did before, you will see this ends up being the span of only 2 non-zero vectors, 1, 0, minus 1 and 0, 1, 2. Okay, the third guy becomes 0. So you can as well drop it from the span. Usually you don't write 0 in the span, right? So you just drop it and then only have 1, 0, minus 1 and 0, 1, 2. Okay, so we see that the span of the columns in this case dramatically changed. I changed the number 6 to 5 here, and then suddenly the span, instead of being 3 dimension, becomes 2 dimension. Okay, so a, b, 2b minus a. How did I get this? So you just multiply the first vector by a, multiply the second vector by b, and add the 2, you get an arbitrary vector in the span, right? So what is that? So a multiplies this, so you get a, b multiplies this, you get b, the last thing, a multiplies this, b multiplies this, so you get 2b minus a. Okay, so this is the column space, the dimension 2 column space, a times this guy plus b times this guy. Okay, the second vector. All right, so this is the span. So remember, previously in the last example, we got the span to be the entire R3. Okay, so now the span is not the entire R3. So there are some elements which do not belong to the span. Span does not cover the entire R3. Okay, so that brings you into this special situation where you see that solution is possible only if the RHS, right, the RHS that we saw here is of the form AB 2B minus A. So in this particular case, it's exactly that form, right? A is 3, B is 6, 2B minus A is 9, right? 12 minus 3 is 9. Okay, so because we got that form, you ended up having a solution. And why would the solution be infinite? Okay, this is dimension 2. Why would you get a dimension 1 there? It ends up happening in this case. We will see later on more general results as to why it has to happen. But this is also an interesting observation. When the dimension of the span reduces by 1, it appears that the dimension of the solution increases by 1. Okay, seems to have an interesting trade-off here. We'll see that also a little bit. Okay, but only when they exist, when the solution exists. But when you have these kind of issues, you can easily see if the RHS is not of the form AB 2B minus A, then there will be no solution. Okay, so that's the third example I have cooked up for you. Here is an example where the matrix remains the same, 1, 1, 1, 1, 2, 3, 1, 3, 5. Instead of 3, 6, 9, I've made it 3, 6, 8. Now I know already from the previous thing that this should not have any solution. Sure enough, if you go through and do the usual method, you get your wonderful 0 equals minus 1 contradiction, which means there is no solution for this problem. Okay, so here again, if you do the same linear algebra view, you get a dimension 2 thing. And if the RHS is not of the form AB 2B minus A, then there is no solution. Okay. So I want you to think about a few things that we did here. We took a 3 by 3 system of linear equations, a simple equation, and then we solved it by some means. We got 3 different types of answers. In one case you got a unique solution, in one case you got infinitely many solution, and in the final case you got no solution. Okay, so these were the 3 cases. Now we took a step back and took a higher level linear algebra view of the whole problem and asked a span membership type question. We looked at the columns and we said the linear equation is actually trying to solve whether the RHS belongs to the span or not. So let's try and understand the span better. We did elimination on the span, tried to find a simpler basis of the span, and it looks like whenever the span has dimension less than the maximum possible, something interesting happens, right? You may have a solution, may not have a solution. When the dimension is entire, then you have a solution all the time. Okay, so we'll stop with this lecture at this point and continue in the next one. Thank you very much.